Okay, so let's discuss the structural anatomy of the lens. As you can see, so far you used to call this structure as lens, and now you have to call it the crystalline lens. And so far you only knew that this nucleus has a capsule and it has a cortex and it has a nucleus. But now you should know something more. You should know that there is, apart from the capsule in which the lens is resting, there is also what we call as the anterior epithelium of the lens. And revising your previous knowledge, this is the cortex, and this is the nucleus. Now let's highlight about the nucleus. When you were in the embryonic stage, the part of the lens or the nucleus fragment was only the embryonic one, and later it developed into a fetal nucleus. And that was in the fetal stage. Now the next element is the infantile nucleus. So when the child or the person is at the age of 1 year, the part of the nucleus that develops is the infantile nucleus. And the final stage into which the nucleus reaches is the adult type of nucleus. And that completes the structural appearance or the structural divisions of the nucleus. So we knew the cornea was a single structure first, then we divided it into 5 layers, and similarly now we are dividing the nucleus into anterior capsule, the anterior epithelium, the cortex, and nucleus. That is 4 layers, and the nucleus is further divided into another 4 layers. Now with regard to nucleus, there are a lot of mathematics or numbers you have to know. To start with, the equatorial diameter, that is, how is the nucleus vertically. This varies in birth and in the adult stage. At birth, this is around 6.5 millimeters, and as it reaches in the adult stage, it doubles up to 9 to 10 millimeters. The adult size reaches by the second decade or at the age of 20 years. Now we have measured the vertical diameter or the equatorial diameter. Equatorial diameter is the distance between or the extent between the two equators, that is the superior equator and the inferior equator. Equator is the point where the anterior surface meets the posterior surface of the nucleus. So this is the equatorial diameter, which is 6, and in the birth and it doubles up to 10. Similarly, the anterior extent is 3.5 at birth and it doubles to 6 millimeters in the adult stage. That is, it doubles itself from 3.5 to 6 millimeters. With regard to the shape of the nucleus, it is an oblate spheroid, which means it is not a perfect sphere. It is an oblate sphere, that is a mixture of a circle and an oval surface. So this mixes up to form a oblate, that is part of a front circle, part of a circle at behind and part of a oval in front, which makes it a oblate spheroid. To be more precise, I think it will be best to put the oval part in front and to put the sphere at behind. So this is how the oblate spheroid in the lens looks like. Now coming to the weight of the nucleus, we should know that it measures around 100 milligrams at birth and triples up to 300 milligrams by the adult size. You should just know a rough weight, because if the statement is like the weight of the nucleus or the weight of the lens is 300 milligrams at birth, then you should definitely be able to say that that's wrong statement. So you don't have to remember it precisely to be 65 or 90. You can just remember that it's around 100 at birth and by the adult size is the maximum weight is around 300 milligrams. And the rate of increase in the weight is around 2 milligrams every year. Now the next is with regard to the radius of curvature. The anterior surface is 8 to 14 millimeters and the posterior surface is around 4.5 to 7.5 millimeters. So the anterior surface, as we have already discussed, this is part of a oval and the posterior part is a circle. So obviously the anterior part is having a greater radius of curvature, that is around 8 to 14 millimeters, and the posterior part is a smaller circle, that is around 4.5 to 7.5. To make it easier, this is 4 to 8 and the next is from 8 to 16, that is double of it. So 4 into 2 is 8 and 8 into 2 is 16. You can remember it that way also. Now this end of the lens is called as the posterior pole. That is the posterior most end of the lens is called as the posterior pole. Now this is the anterior pole. Now this is the anterior pole of the anterior surface and this is the posterior pole of the posterior surface. So the line joining the anterior pole and the posterior pole forms the optical axis. Now coming to the equator, the equator is that part of the lens where the posterior surface and the anterior surface actually meets. Now the equator is actually encircled by, so if you, let's say if this is the equator of the lens, it is completely encircled by the zonules that arise from the ciliary body. And at the point where these zonules get attached to the capsule are called as indentations, are called as dentations. With regard to the refractive index, we should know that it is actually the nucleus that has the highest refractive index of about 1.41. At the poles, it is around 1.38, and at the equators it is around 1.37. On an average, it is somewhere around a little more than the cornea. Cornea is around 1.37. So the refractive index of the lens is more than that of the cornea, and on an average this may sum up to 1.38 or 39. But most importantly, the question usually arises is about that of the nucleus. So you should know that the refractive index of the nucleus of the crystalline lens is around 1.41. And as you already know, the refractive power of the lens is 18 diopters, or on an average to a range you can say that it is around 16 to 18 diopters. With regard to the accommodative power of the lens, you should know that this is the non-accommodated, this is the with regard to accommodation, you should know that when the lens is getting focused to a distant object, it is in a relaxed state. That means you can see that the thickness of the lens is moderate or it is normal, and the ciliary muscles on this end, at this end, are relaxed. But when the eye is getting focused to a nearby object, the thickness of the lens increases. This is because of contraction of the ciliary muscles, which are located in the ciliary body. So it is through the contraction of the capsule, or by the contraction of the ciliary muscles through the zonular attachments on the lens capsule, the mechanism of accommodation happens. So in an accommodated state, the lens thickness is more due to this mechanism, and in a relaxed state, the lens appears thinner because the ciliary muscles are relaxed. Now this is the cross section of the eye. You can see that it is the movement of the ciliary muscles which helps in the changing of the lens size. So now how much is the accommodative power that the eye gets during accommodation? At birth it is very high, that is around 14 to 16 diopters. And as age increases, the accommodative strength of the eye keeps decreasing. That is, by the age of 25 years, it drops to almost half. From 16, it drops to 8. Or if you want a range, from 14 to 16, it almost drops by half, coming to 7 to 8 diopters. And from that stage, it is almost cut down to 1/4 by the age, as the age doubles to 50 years, and that comes down to 1 to 2 diopters. So when a person is reading at the distance of 30 centimeters, he will definitely require a help of or the aid of a glass for accommodation while reading. Now coming to the change in the lens color as the age progresses. At birth or during infancy, the lens is transparent. During adult age, it is transparent. And as the age gets to 30 years, it starts getting an yellow tinge. So what I would like to specify here is, by the age of 30 years itself, the eye gets a yellowish tinge. So the presence of an yellowish tinge should never be misdiagnosed to be a cataract. Cataract means there will be a sclerotic change in the nucleus or the other parts of the lens. And in an older age, it becomes into a amber color. So this is an age-wise depiction of the color of the nucleus. That is, at the age of 6th month, it is transparent, and by the age of 30, it starts getting an yellowish tinge at the center, and gradually it progresses to become dense and thick to brown. So now let's discuss the anatomical position of the crystalline lens. Anterior to the crystalline lens, we see the pupillary aperture, that is formed by the iris. At this end, and this is the posterior surface of the iris that is in close association with the anterior surface of the lens. This part. Now the lateral end of the crystalline lens. Now this is the cross section. Now if you imagine it to be in an anterior view, we have to know that the lateral part of the crystalline lens is associated with the zonules, and these zonules attach the lens to the ciliary processes all around. Now the posterior surface of the crystalline lens is now placed between the iris and the vitreous. And this lens is attached posteriorly to the vitreous in a circular manner through the Vegas ligament. There is a strong association between the posterior capsule and the vitreous here. This is called as a Vegas ligament. Now between the hyaloid face and the lens capsule, there is a small potential space called as the retrolental or the Berger's space, which is in this area. It's a potential space. And the space that exists in the lateral ends of the lens is called as space of Garnier. Now the structures forming the lens is the lens capsule, the anterior lens epithelium, and the lens fibers. So the nucleus and the nucleus and the cortex is having the lens fibers and the anterior lens epithelium along with the anterior capsule all around. Now coming to the lens capsule, the lens capsule is a thin, transparent, hyaline collagenous membrane. It is surrounding the entire lens completely. Elastic in nature, but it does not contain any elastic tissues, which is a mystery. Now anteriorly secreted by the lens epithelium and posteriorly by the basal cells of the elongated fibers. As you know, there are lens epitheliums located in the anterior part of the lens. So it is this lens epithelium that secretes the anterior part of the lens capsules. And there are basal cells here which forms elongated fibers which secretes the posterior part of the lens capsule. Now the type of collagen is important. Here it is type 4 collagen along with glycosaminoglycans. It's important to know the thickness of the lens capsule. You should know that it is thinnest at the posterior pole and thickest at the paracentral surface. Anteriorly it is around 14 microns At the equator, it is 17 microns. At the paracentral areas, like this is the central and adjacent area, these parts of the capsule are the thickest, which is around 21 to 23. Another fact to know is that the lens capsule is actually a form of basement membrane, and it would be surprising to know that this is the thickest basement membrane you can find in the body. With regard to diseases affecting the capsule, you should know that there is something called as true exfoliation. True exfoliation and pseudo exfoliation. So true exfoliation is actually seen in glass blowers because of a true exposure. In glass blowers who works in a high temperature producing factories with infrared radiations. So these can cause melting or peeling off of the anterior or the posterior capsule. And it is the superficial zonular lamellae of the capsule that splits off and peels off. But there is another entity similar to this, which is called as the pseudo exfoliation. So as the name suggests, this is not a true heat induced peeling of the capsule. It's in fact an appearance wherein it looks as if the capsule has been peeled off. Now this happens because of deposition of fibrillogranular white materials that gets deposited on the entire structures in the eye, which includes the lens, the cornea, the iris, the anterior hyaloid phase, the ciliary processes, the zonular fibers, and also the trabecular meshwork. And ultimately, this deposition in the ankles results in glaucoma. Another clinical significance with regard to the capsule is the imprinting of iris pigments that you see on the anterior capsule. Now this is usually following a blunt trauma. At the time of impact, the pupil undergoes meiosis and inflammation, because of which the pigment imprints of the iris imprints on the lens, and later it gets traumatically dilated, and the area of imprint is very well evident on the anterior capsule.